We are interested in checking the convergence and divergence of the following series. Here you have the summation of k sine squared of k divided by 1 plus k to the third, and my k starts from 1 goes to infinity. So what I'm going to do, I'm going to use comparison test. Why is that? Because it's easier for me to compare this series with a p series. Take a look. It is easier for me to compare this series with a p series. What p series? Let me show you. When you see sine, cosine function, it's better to use their boundaries. Remember that. You have sine to the second power. Sine squared is always bounded between -1 and 1. When you raise it to the second power, it's bounded between 0 and 1. Since sine squared of k is bounded between 1 and 0, so we can find an upper bound for the general term. Take a look. Here I have k times sine squared k divided by 1 plus k to the third. This guy is less than equals to k divided by 1 plus k to the third. You could also do algebra, right? You could see it this way. You can say that, hey, since sine squared of k is less than equals to 1, if I multiply both sides by k, I get k times sine squared of k less than equals to 1 times k. And then I divide these by 1 plus k to the third. All of these are positive numbers. So you're allowed to do multiplication and division. So basically, the series on the left-hand side is comparable with the series on the right-hand side. But note that at the same time, 1 plus k to the third is more than k to the third. So if I flip this 1 over 1 plus k to the third is less than 1 over k to the third. And if you multiply everything by k, k divided by 1 plus k cubed is less than equals to k divided by k cubed. But this guy on the right-hand side is equal to 1 over k squared. So this guy is less than 1 over k squared. So now we see the p series, the summation of 1 divided by k squared. Okay, let us rewrite this guy down here. K sine squared of k divided by 1 plus k cubed is less than equals to 1 over k squared. Remember, comparison test. The comparison test says if an is less than equals to bn, and if the larger series is convergent, then for sure you can conclude that the smaller series is convergent as well. So since the series on the right-hand side, the summation of 1 divided by k squared is a p series, and p is equal to 2 more than 1 is convergent, it means that the smaller series on the left-hand side must be a convergent series as well. So the summation of k times sine squared k divided by 1 plus k cubed is also a convergent series by comparison test. So wherever you see sine, cosine, sine squared, cosine squared, it make it easier to use comparison test because you can always find a p-series to compare your original series with that. In this case, I did algebra. I took sine squared of k. Sine squared of k is always less than equals to 1. So what do we have? We have multiplying k squared of k by k, so you get k times sine squared of k less than equals to 1 times k. And on the denominator, if you divide by 1 plus k cubed, it doesn't change these inequalities. Why is that? Because they are all positive numbers. But at the same time, 1 plus k cubed is more than k cubed. If you divide these two by 1, you have to flip the inequality. You end up with k divided by 1 plus k cubed less than k divided by k cubed, or this guy on the right-hand side is nothing but 1 over k squared. So k divided by 1 plus k cubed is less than 1 over k squared. It means that the fraction on the left-hand side is less than the fraction on the right-hand side, or basically you can compare series on the left-hand side to the series on the right-hand side. Based on comparison test, if the larger series is convergent, the smaller series is convergent as well. But 1 over k squared is nothing but a p-series. P is equal to 2. 2 is more than 1. You get a convergent series. So it means that your smaller series is also a convergent series as well.